Hey, welcome. Today, we're tackling a really fundamental question in statistics, one that trips up a lot of people. Is your data normally distributed? Now, I know, it sounds super technical, but trust me, getting this one wrong can pretty much sink your entire analysis. So, let's find out if your data is playing by the rules.
So here's what we're going to cover. First, we'll talk about why this even matters. Then we'll look at the two main ways you can test for it. We'll get into the whole p-value thing, but then, and this is the important part, we're going to uncover a huge problem with it. Finally, we'll see why looking at your data is often a much better way to go, and we'll wrap it all up with your final takeaway.
Okay, so first things first, why do we even care about this normality check? Well, it's because a ton of the most common, most powerful statistical tools out there, they all rely on this one hidden assumption about your data. And before you can trust the results, you've got to make sure that assumption holds up.
I mean, think about it. You're all set to run a t-test or an ANOVA. You're hoping to find something significant, something cool. But hold on. These tests have a kind of fine print, a prerequisite you just can't skip over.
And that prerequisite is the normal distribution. You've all seen it, right? It's that classic symmetrical bell curve. It's just a pattern where most of your data points are all clustered right around the average, and then they get less and less frequent as you move out to the sides.
And here's the bottom line. If your data doesn't roughly fit this shape, those statistical tests can lie to you. Seriously, they can give you results that are totally off, making you think you found something amazing when you haven't. Or, maybe even worse, making you miss a real discovery that's sitting right there.
All right, so how do we actually check for this? Thankfully, we've got two main ways to figure out if our data is behaving itself.
You can go down the analytical path, the one with hard numbers and formal tests. Or you can take the graphical path, which lets you literally see the shape of your data. Let's start with the numbers first.
Now, this is the way a lot of us first learn to do it. It's all about getting that one single number, the p-value, that's supposed to give you a clean, simple yes or no answer. And you've probably bumped into these names in whatever stat software you use. The Kolmogorov-Smirnov test, the Shapiro-Wilk, maybe the Anderson-Darling. They all sound complicated, but they all work on the exact same idea. And that big idea is the null hypothesis. It sounds kind of formal, but it's really simple. The test just starts off by assuming your data is normal. That's its starting point. The whole job of the test is to see if you have enough evidence to call that assumption into question.
And the process is always the same drill. First, the test says, okay, let's assume the data is normal. Then, it does its calculations and spits out a p-value. And finally, you take that p-value and compare it to a cutoff point that you decided on beforehand, which we usually call the significance level.
And that cutoff, that magic number that you see everywhere in science, is almost always 0.05. This is our line in the sand.
So the rule is pretty straightforward. If the p-value the test gives you is less than 0.05, you get to reject that initial assumption. You found strong evidence that your data is in fact not normally distributed. If it's bigger than 0.05, you basically say, well, I don't have enough proof to say it's not normal. Seems simple, right? Not so fast.
And here is where our nice, clean story gets a huge wrinkle. This whole analytical method has a massive flaw, and it all comes down to how much data you have.
See, the giant problem here is that the p-value isn't just measuring normality. It's also super sensitive to your sample size. And this creates this incredibly frustrating paradox that can really lead you astray.
So if you only have a small sample, these tests are kind of weak. They don't have a lot of power. They'll almost always give you a big p-value, way above 0.05, even if your data is actually pretty weird looking. The test just isn't sensitive enough to spot the problem. But on the flip side, if you have a huge sample, we're talking thousands of data points, the test becomes too sensitive. It can pick up on the tiniest, most insignificant little deviation from a perfect bell curve and give you a p-value of like 0.001. It'll scream, this is not normal, when for all practical purposes, your data is totally fine to use.
So, if the p-value is a trap waiting to happen, how do we get out of it? Simple. We use our eyes. The graphical approach gives us all the context and nuance that a single p-value just throws away.
And the absolute best tool for the job is something called a QQ plot, which stands for quantile-quantile plot. All it does is this. It plots the distribution of your data against what the distribution would look like if it were perfectly normal. It's a direct comparison.
And reading one of these is actually beautiful in its simplicity.
If your data is normal, the dots are just going to hug that straight diagonal line really closely. But if they start to curve away from the line, maybe making an S shape or an arc, that's a dead giveaway that your data isn't normal. It doesn't just tell you if it deviates, it shows you how and where it deviates. That's so much more useful.
Okay, let's pull all of this together. When you're standing at this crossroads, looking at the numbers on one side and the pictures on the other, what's the final call?
Well, it really comes down to this trade-off, right? The analytical tests, they give you that hard, definite p-value, which feels objective, but we've seen how they are dangerously sensitive to how much data you have. The graphical plots, on the other hand, give you that crucial context and let you see the bigger picture, but yeah, they do require you to use your own brain and make a judgment call.
So here's what you absolutely need to remember. 1, p-values from these tests can be incredibly misleading. 2, if you have a lot of data, they're going to find tiny, meaningless problems. And 3, and this is the most important one, you should always back up a numerical test with a visual one. Make that QQ plot your best friend. So that really leaves us with one final critical question you should ask yourself every time you do an analysis. Are you just listening to a single p-value, or are you truly looking at your data? The real story is almost never in one number. It's in the shape, the pattern, the context. Trust your eyes.